Thanks, Juan, and thank you very much to the organizers for inviting me here. I've gotten quite a lot out of this meeting so far. Before I begin, I want to acknowledge my co-author, Craig Bishop, who's at the Naval Research Laboratory. Much of the work that I'm going to show was done in collaboration with Craig. A couple of people that are not on the author list, but that I want to acknowledge as well, are Dan Hodis, who's also at the Naval Research Laboratory, and then also Tomislava Vukicevic, who's recently moved to the NOAA Water Center. So I want to just set the stage a bit here, talking about what I mean by model parameters. In particular, I'm going to be talking about parameters that are defined within a model as a result of simplification of processes. And so in particular, I'm dealing with parameters that are related to microphysical schemes. So the fact that we can't explicitly resolve the finest scales where the particle interactions take place, and so we need to parameterize those. And so I'm considering those as a control on a set of cloud processes. And so if we think about this in terms of controls and outcomes, and I'll return to this in multiple times through the talk, this idea of sort of a variation and a response. These microphysical parameters, if you change them, they may have an influence on things like cold pools underneath convection, updraft and downdraft strength, the amount of latent heating, vertical condensate distribution, radiative fluxes, etc. Now, interestingly, if you change these things because of a change in parameters, then this may also feed back on the microphysical processes themselves. And so there's some complexity here that we need to deal with. So like I said, I'm specifically dealing with microphysical parameters. And the goals of the research that we've been doing are to assess and quantify the uncertainty in model parameterizations for a number of reasons. You might want to do this because you want to estimate model error more appropriately and or produce larger range of ensemble realizations. You may want to tune your models, optimize parameter values for a particular system or another. Or you may just want to learn about your parameterization scheme to provide guidance for model development. And then finally, and this is work that I won't show as much here, but we've been doing much more lately, examining the actual physical characteristics of the system themselves, using data assimilation as a tool to do that, of course, as viewed through the lens of an imperfect model. Now, the challenges here are that many of the parameters that we care about are quite nonlinearly related to the response of the system, and I'll show that in just a minute. The other challenge is that we tend to specify parameter values globally, but we know that there are probably regional differences and state dependence of the values that we ought to be estimating. So another source of, and I can represent that by sort of illustrating a range of different cloud systems, for example, each of which may have very different sets of microphysical parameters that exert control over their outcomes, and perhaps very different parameter values. Okay, so going to the data assimilation framework, again, we have our questions here, which, in my case, which of the cloud parameters contribute most to model uncertainty? And then the question is, how do those uncertainties change with model dimensionality and with region and context? And then what I'll show in the second half of the talk is some results on evaluation of ensemble data assimilation algorithms for reproducing a more exact Bayesian posterior distribution. Just the context here, we consider a vector of parameters x, that's my control, and I have a set of responses, things I care about, output from the model, precipitation rate, radiative fluxes, etc., which I'll define as a vector y. And then, as you've seen many, many times in this symposium, we're basically attempting to solve Bayes' theorem, the non-normalized version of which is here. And so I'm going to be estimating a posterior distribution of my parameters given a set of observations or responses, and then for which I will need a likelihood and a prior. So I want to spend a little bit of time talking about methodology because this is something that perhaps hasn't been covered as much in this symposium, but I'm going to be using Bayesian methodology. So again, our goal is to estimate a posterior distribution given a likelihood and a prior. So we have several options. We can assume a distribution, Gaussian or the like. Another option, if we have a low-dimensional parameter space, is we could just compute that distribution by brute force. So we can divide our parameter set up into discrete ranges and then compute a likelihood and a prior for every single one of those bins. And basically then we obtain a representation of our likelihood and our posterior distribution. Problem is this is very computationally expensive, not really feasible for more than a 2 or 3 dimensional problem. So another option, and this is of course what's done in particle filtering and also can be argued in ensemble Kalman filtering, is you generate a Monte Carlo sample. So you say, I'm going to generate an ensemble, and I'll use that ensemble to tell me something about the posterior distribution. The problem with this is, of course, the dimensionality, and lots of very good progress is being made in that direction via localization and other modifications to Monte Carlo sampling, but it remains a bit of a problem. So an option that hasn't been discussed as much, and which I'll talk about a little bit here, is to construct a Markov chain that samples the posterior distribution. And this is at the core of what's done in Markov chain Monte Carlo algorithms. And so what these algorithms do is they produce a sample of the posterior distribution by guiding the walk of that random Markov process so that it continually revisits relatively high likelihood regions of the posterior PDF and avoids low likelihood regions. This beats down on the problem of dimensionality in the system as it avoids regions of the space that have low probability. And you can show that it converges nicely to sampling the exact posterior distribution. I won't talk much about the derivation of Markov chain Monte Carlo. I'll be happy to talk more about that afterwards if folks are interested. One of the key things about Markov chain Monte Carlo is that it's entirely flexible in terms of what you specify for the probability distributions. So I don't have to assume anything about my likelihood. I don't have to assume anything about my posterior distribution. It gives me freedom to choose whatever I think is most appropriate for the problem that I have at hand. Okay, so the particulars of the scenario that I'm looking at, I'm looking in particular at squall line simulations. So these are two simulations, early, middle, and late in the development of a convective squall line viewed from the side. So developing phase, mature phase, and a dissipating phase. The colored contours here correspond to cloud condensate. Open contours correspond to vertical velocity. And this on the bottom is just a reference simulation run at very high resolution, just to show you that my coarser resolution runs are an approximation to this. Now, most of the results that I'm going to be showing come from a one-dimensional approximation to this model. I have a column model that I essentially drag through this convective system, forcing it to act as if it were embedded in convection by specifying a vertical velocity and a moisture and temperature tendency. Okay, so the parameters that I'm looking at are ones that are common in bulk microphysical schemes. I have 10 of them. These are parameters that determine, based on an assumed crystal shape for snow and graupel, how fast ice particles fall. That's the first set of 4 of these. Okay, and then there's 2 warm rain parameters, and the next talk will cover some of these in some detail. But at what point do I decide that I have enough cloud mass that it should be dumped into rain and precipitated out? What should my rain particle size distribution look like? And then my ice particle size distribution and my ice particle densities. I'm going to use as my observations 5 different output variables. These are ones that not only are commonly estimatable from retrievals from spaceborne platforms, but also ones that we care about from both a weather and climate perspective. So I'm using precipitation rate, liquid and ice water path, and outgoing long wave and short wave radiation. And I've specified errors on these, or uncertainties, consistent with what we might assume we get from satellite retrievals. Modifying those errors in just a little bit, we'll talk about that in a second. Okay, again, these observations are climate relevant. I want to just mention before I get going that these first set of experiments, I'm going to assume for my prior that have a bounded uniform distribution on my parameters. I know nothing about their probabilities except that they must lie within a physically realistic range. Bounded at 0 at the low end, and this will become important, and then bounded at the high end by a value that I've estimated from multiple measurements of these kinds of parameters taken in situ. So before I get going, I want to show you a little bit of what the response function to these parameters looks like, and this sets some of the context for the complexity of the problem. So I'm going to choose just one parameter, the graupel fall speed coefficient, and one output variable, the precipitation rate. And what I'm doing here is I'm plotting the response of the rain rate to changes in my parameter. So as I increase the fall speed coefficient, graupel particles fall faster, and I get more rain. Okay, so this makes a lot of sense, and my response function looks smooth, and so far it looks like I might use any number of algorithms to be able to do the data assimilation problem here. It gets tricky once I get to later and later in the simulation. Once the ice processes really start to have some effect, now I have a non-monotonic response. So I increase my precipitation up to a point, And then after that, my precipitation actually decreases with an increase in fall speed. And I won't go into the details of this. I've got a paper on it. But there are good physical reasons for this. Once I get really late in the simulation, about 3 hours worth of development, then I get a really complicated looking response function. And this is going to cause problems for data assimilation algorithms that assume that I have a constant covariance, for example, between my parameter space and my observation space. I'll show you what that looks like in just a minute. Before I get to the data assimilation, I just want to illustrate that these parameters do influence the model outcome. So what you see here is 10,000 realizations, random realizations of my parameter sets, and their influence then on the outcomes of my model. And this is, again, this is the 1D model, so it's just a column. And so by nature, this is probably larger sensitivity than you would see in a three-dimensional model, or perhaps you'd think that, and I'll get to that in the next slide. But what you can see is that if I vary just my microphysics, I'm not varying the environment at all, I get a very large range of precipitation rates, ice and water contents, and a rather huge range of radiative fluxes here. Okay, these really are on the order of hundreds of watts per meter squared in both my radiative transfer rates. Okay, if I go to a 3D model, this is an article that I'm writing up now where we compare the influence of microphysics to the influence of initial conditions. So my initial conditions plots are in this gray here, and my microphysics are in black. This is for a three-dimensional cloud resolving model, another 10,000 member ensemble with random parameter realizations. So in gray, I'm holding my parameters fixed. In the black, I'm varying them. And the range of values here is different because I'm averaging this over the simulation domain, which is why the ranges are smaller. But you still see a very large range of outcomes based on a change in just my microphysical parameters. So these things are important. They have an influence on my simulation. Okay, so what I'm going to show you now in the next few slides are two-dimensional marginals through a 10-dimensional PDF. Okay, kind of tough to visualize a PDF in 10 dimensions, so we have to reduce it. So I'm going to show you marginal distributions in 2 dimensions. So I'll have 2 parameters, okay, and the contours will illustrate the probability density. So remember, I have a bounded uniform prior. If you see a bounded uniform posterior, it means that the parameters had no influence on the solution. It's pretty straightforward. Bounded uniform prior, if I see something that's not bounded uniform, it meant my prior, my parameters had an influence on the model solution. Okay, and in this case, there was a fairly large degree of influence, and the parameters are correlated. In some cases, I may have a bimodal distribution here, and if you think back to the response function, what this means is that for one set of parameter values, I had a rising set of outcomes, and for another set of values, I had a falling set of outcomes. What that means is that there are 2 sets of parameter values that gave me the exact same outcome, and it leads to a multimodal PDF. Let's go to the results. I'm going to summarize these pretty quickly because I want to get on to the ensemble algorithms. So these are a set of 4 of those 2D marginals, just showing you what kind of outcome you get. What I basically did here is I assumed I only had observations of my hydrologic cycle, didn't have observations of outgoing long wave and short wave radiance. I'm not going to get into the interpretation. What I want you to focus on is the observability of the parameters, right? So if I use observations from satellite, how well do I constrain those parameters? If I get a unique mode that's located around the truth, I can say that I've done a pretty good job. In this case, not really well constrained in terms of what I'm observing. And actually, I'm going to go ahead and replace observability by identifiability, because I think it's actually more what I'm after here. I know that I have observations that are related to these parameters. The question is, do those observations correctly identify the parameter values that I'm after? Okay, so let's go ahead and add observations of radiative flux to this and see how that changes the posterior distribution. And if I flip back and forth between the two, you can see that the radiative flux does start to help to constrain certain aspects of my parameter values, so that's helpful. I do have a sense that I'm not quite there yet because my PDFs are rather diffuse. I have diffuse probability, and in some cases my mode might not be exactly at the truth, and so I think, well, in this case, if I use more accurate observations, maybe that will help. So I reduce my radiative flux observation errors to about half of what they were. This is consistent with what we're doing in terms of satellite observation development. We get better. Now what's interesting is just by reducing the ob error variance, in fact, I don't help myself. I make things much, much harder. And now, in fact, I have a multimodal distribution where I used to have a single mode distribution. Here's where you start to learn something about what your algorithm does. And I have in the dashed lines here the solution I would get if I interposed, if I changed snow and called it Grapple instead, or if I changed Grapple and called it snow. And inside my microphysics code, I can do that, and the model doesn't know any different. And so I have a non-unique solution just because of the way that my microphysics was constructed. So having learned that, what I can do is I can say, well, I'm going to apply a physical constraint. I require a heavier ice particle, a more dense ice particle to fall faster. So I say Grapple has to fall faster than snow. And here's what I get in terms of my outcome. So I've used my 5 observing system variables. I've assumed uncertainties consistent with a near future observing system. And now I have most of my parameters identifiable using my observations. OK, so I've gone through the exercise of determining what the posterior PDF looks like. However, I've used an algorithm that requires many, many hundreds of thousands of iterations to sample that posterior PDF, which means that I'm not going to ever use it in reality in an ensemble DA kind of system. But it's been useful because now I know the posterior distribution of those parameters, and I can say, if I use a more approximate algorithm, what is the solution that I might get? And so that's where I'm going now. So MCMC gives me a sample of the unapproximated posterior distribution. And now what I'm going to do is I'm going to use that to evaluate the capability of ensemble filters to estimate my model physics parameters. Okay. So I'm going to use 2 algorithms here. Did a couple of studies where we evaluated a perturbed Dobbs ENKF. This is actually a perturbed Dobbs ensemble transform. We have also evaluated the deterministic ensemble transform. I won't have time to show you all of that. And then the most recent results we're getting from an algorithm that Craig Bishop came up with last year. We're calling a inverse gamma filter. I want to make clear that what I'm doing here is a single analysis update. I'm not cycling, as we would typically do with an ensemble algorithm. And so in all of my results, that cycling and the benefit that you get of sequential accumulation of information isn't going to be in what I'm showing. I'm just showing a single analysis update. So I want to give that caveat. OK, so perturbed Dobbs ENKF. These are the equations, both for the analysis mean and for one of my ensemble perturbations here from the analysis. These equations are all familiar to us all, I'm sure. And so what I do is I use these equations to give me a posterior distribution for my parameters. And then I can interrogate that to see what it looks like. And then I can say, if I change my parameter values, the true values, then how does the posterior distribution change? And does the ENKF track those changes in a realistic sort of way? OK. So here's using MCMC to parameters. I have my warm rain parameters, and I have my ice parameters. This is, again, out of a set of 10. I'm just showing you 2 sets of them for compactness. And I have 3 different experiments where I've set 3 different truth values of these parameters. Now, what MCMC allows me to do is to say, as the parameter values change in reality, the posterior distribution, does it change? Does it remain the same? And in fact, the posterior distribution changes significantly as I change the true values of my parameters. And one thing that you'll notice about this, which is really rather interesting, is that the variance in the posterior scales with the values of the parameter. So as I go to larger and larger parameters, my variance gets bigger and bigger. And this is kind of an interesting property of this particular system. If I go to ENKF, I do see some things that are realistic. Okay, so in particular for my ice parameters, if I flip back and forth, the general shape of the distribution is correct in the posterior distribution, okay? And it's not just a Gaussian. I mean, it knows about the nonlinear dynamics of the model, right? And so it's not just giving me back a Gaussian, it's giving me back something with some structure. But the problem that pops out almost immediately is that whereas the analysis mean very nicely tracks the mode and mean of the posterior distribution, the posterior variance doesn't change. The shape of the distribution remains the same. Now, for some cases, this isn't a big deal. If the parameter values are rather large, these distributions don't look bad. But as my parameter values get closer and closer to 0, what you notice is that more and more of my posterior analysis space lies in unphysical territory. Okay, I'm getting negative parameter values. What's going on here? So if I go and I look at the MCMC for ice versus the ENKF for ice, and I sort of blur my eyes here, it kind of starts to look like maybe the ENKF might be looking like an average over all possible prior parameter values, right? And in fact, if you look at the ENKF equations, that's essentially exactly what it is. So to test that hypothesis, what I do is I draw 100 sets of parameter values with the simulated observations. I run MCMC 100 times to get a set of posterior distributions. I remove the mean. I accumulate what remains into a grand unified distribution. And then I compare. So here's what I get. And in fact, it does appear that the NKF is looking quite a lot more like the analysis I would get if I integrate over all possible true values of my parameter sets for this particular algorithm. It's a little bit overvariant, and we think that's because it's not accounting for the higher moments. And in fact, you can test that by using an algorithm that accounts for the third moment. This is Dan Hodis's quadratic ensemble filter, and it does get closer to the MCMC solution. Okay, so that's for the NKF. So I get a successful tracking of the ensemble mean, but if I look at my analysis distribution, nowhere in here is the actual observation. It just knows about the ob error and the prior, and so of course it's going to form me the same shaped ensemble no matter what I do, but it will shift the mean because the mean depends on my actual observation value. So it's doing a good job tracking the mean. It's not giving me a knowledge of the fact that my parameters are positive definite. I want to say the caveat that if I were to give it a more informative prior, it's entirely possible the NKF could have produced a more robust solution. It's one of the things that we show in one of our papers. Again, I won't have time to show it here. The final thing I'm going to show you is results from this inverse gamma filter. This is in a paper by Craig Bishop in QJ in 2016. He came up with a unified formulation where you could have Gaussian gamma or inverse gamma PDFs. These all have a unit variance but different mean. So with the Gaussian, shape remains the same, doesn't matter what the mean is. But with the gamma and inverse gamma, the shape of the distribution depends on the mean, which is kind of interesting. So this isn't maybe right for all problems, but it might be right for ours because it accommodates parameter values that are hard-bounded at 0, very, very naturally. It also, the shape of this scales nicely with the value of the parameter. So that's another sort of nice property and maps nicely onto my solution. So I'm going to skip through the derivation of this. This is just a number of different gamma parameters to show you what the various shapes look like. And I'm going to show the results of a fairly simple experiment where I just estimate 2 parameters, the warm rain parameters, for 3 different precipitation rates. And I look at MCMC, ENKF, and the gig. So here's my posterior distributions in observation space. I have the large observations, moderate, and low observation values, okay? And here are the posterior distributions. The gray is the prior, the black is the posterior, and what you can see is that MCMC is giving me something with some skewness. The gig is tracking that relatively nicely. Note the change in the axis here from 30 to 15. The NKF distribution not changing shape, but it is relocating the mean, so consistent with what the algorithm is supposed to do. With the gig, because it's instead of applying a constant ob error variance, it's counting for the relative ob error variance, it's scaling the distribution appropriately as I go to low and lower observation error. So I'm getting no posterior observations in negative space. My posterior variance is tracking nicely with the Bayesian solution. Okay. I'm going to highlight this one especially because this shows very nicely the fact that the gig is doing a quite nice job at low precipitation values. Okay, so now if I look at the posterior distribution in state space, so the gig is formulated in an ob space, and having a formulation in ob space, we need to regress to state space to get back my actual parameter values. You'd need to do this if you were going to be running an ensemble based on the gig analysis. This is similar to Jeff Anderson's ensemble adjustment Kalman filter, which also requires a regression back to state space. So here's the MCMC state space. As with my earlier experiments, the shape of the distribution changes based on my parameter values. So here's my true parameter values, and here is the shape of the posterior distribution. Here's the ENKF. As with my previous results, the shape doesn't change, but the mean does with different parameter values. Okay, and here's the gig. Now, it doesn't look great, but at least in this first regression, the shapes are starting to track what you see from the MCMC. It knows a bit about the fact that it should be tightening up the posterior distribution. But the thing is that when you look at, you run that state space distribution into ob space, you see problems. So the black here is my ob space analysis produced by the gig, the ENKF, and the MCMC. The red is what I get when I run my state space analysis into observation space. They should be consistent if the 2 analyses are consistent, state and observation space, and they're not. especially for the low parameter values. I get a lot of members near 0. Don't capture the variance properly. I have a gross inconsistency here. So the question is why? And if I look at the response functions for my variables, good, I'm just about to wrap up, I see complexity here. So this is the response of the precipitation rate to a change in a parameter. This looks fairly well behaved, but for my other warm rain parameter, I see a change in covariance depending on the value of my other parameter. This is causing problems. So in theory, what I could do is I could localize this, right? I could say, if I know that my state space is probably about here, I'll just regress using those members that are close to it, localize that regression from ob space to state space, and I should do better. Okay, so let's try that. So what Craig came up with was a way to essentially do what he's calling an ensemble outer loop or an ensemble tangent linear, where we weight our regression based on how close the two state space values are. And in the interest of time, I'll just show you what results from this. If I do that iterative minimization and regression, I get an almost perfectly consistent ob space solution. And here's my original state space solution. I get a much, much nicer state space solution for the gig as well. It matches almost exactly with the Bayesian solution, in fact. Okay, so summary slide number 1. Properties of my model parameters, a lot of them are positive definite. Values could be close to 0, and the sensitivity changes according to context. If we use data assimilation algorithms to tune or to estimate parameters, we've got to account for those properties. So I've used C to provide a reference solution. That gives me an assessment of parameter sensitivity and identifiability, and how both change with changes in physical context. Okay, then I evaluate ensemble algorithms. For the ENKF, the distribution mean is approximately correct, but the linear update doesn't capture changes in distribution shape and may in fact produce non-physical negative parameter values. The gig filter, because of the way it's constructed, can represent changes in parameter sensitivity because it knows about the changes in the distribution shape with changes in ob, and it nicely accommodates positive definite parameters and observations. If you apply a weighted ensemble outer loop, that ensures consistency between state and observation space. And I should mention that you don't have to limit that to the gig. We could use that as well for the ENKF. All right, with that, I'll leave up my references and I'll take questions.